Hello everyone, welcome back to Power System ECE360 class number 10. Today we're going to talk about inductance in three-phase line. So last class we talked about inductance in three-phase line with the symmetrical line. That means each phase is equal distance from each other, but now we're going to more generalize it for asymmetrical line. So this is the asymmetrical line here. So line distance from each other is not same anymore. It was D before for all of them, but now we have D12, D13, D23. So this is the general equation right here for total flux linkage for any amount of line going like next to each other. Like that means if you have any amount of line going next to each other, that total flux linkage to any of the line includes the self linkage plus all other linkage coming from other line, as we discussed before. So now if I modify that for this line A right here, so I have two other lines. So we have self and two other lines. So let's put the constant here first. Then, so IA, that's my line I'm looking into. So then I ln 1 over r prime. That means I'm assuming that all the line has the same radius. Plus now we have IB, right? Then natural logarithm 1 over, so line distance between A and B is D12 here. So I'm going to put D12 over here. Plus IC, right? Then natural logarithm 1 over the distance between A and C is D13. I'm going to put D13 here, right? So that's for lambda A, 12 flux linkage to line A. And now you can easily find lambda B here is same constant, right? Then you have you put IA here. Then the distance between B and A is D1, 2, and IB is self linkage here. So it will be ln 1 over r prime here. IB is a self linkage. Then your IC, natural logarithm 1 over C, and distance between C and B is D23, right? So that's, see how easy that is. Then you can also find, if you want, lambda C, it will be same way here. IA ln C and A is D13, right? IB ln from B and C is D23, right? Plus IC is self linkage, so it will be natural logarithm 1 over r prime. So they have the linkage to each of the line, all three of them, right? So now let's need to little bit more manipulation to this equation to find the inductance. All right. The first manipulation I'm going to do here is show you some of the, it's called introducing control factors or a parameters into the line. So let's show it over here. Let's say you have a 3 current over here. You know that all of them are basically 120 degree apart from each other. AIB, and IC. We always use the positive sequence here. So each of them are 120 degree apart from each other, right? You know that. And all of them are same magnitude, right? So let's introduce a parameter here. Is a parameter A is 120 degree. This is the parameter A. So if we have the parameter A introduced here, then A squared would be 240 degree, right? You all know from your complex math. Now, so let's see your IA here. If you compare other two with the IA, your IB over here is basically IA 120 degree, right? So 240 degree. We're going counterclockwise. We're going counterclockwise. So let's travel counterclockwise. So it'll be 240, right? Right? So that means I can also say that is IA times 1 to 40 degree, right? So that means is a squared IA. So IB is basically a squared IA. That's what I'm saying. IB is basically what? A squared IA. Then with respect to IA, if I look at IC over here, going counterclockwise, it's only 120 here. So it'd be IA 120 degree. That means is IA. So with respect to IA, I can convert IBIC to IA. If I do the same thing for IB, if I now look at IB over here, so let's say your IA is 120 degree from IB. So your IA in terms of IB, so it would be, if you can let's see here, you're looking at this one here, you're going counterclockwise. So IA is IA, right? Can you see that? Then your sorry, this IB, right? Then your IC with respect to IB, you have from here to here, you have 240 degree. So that would be A squared IB, right? So here everything is converted into IB, right? Then if I like a different color here, let me show you if I have a different color here. Let's do, which is better? Green might be okay. So let's say we're gonna do with respect to IC, everything would be converted in terms of IC. So IC is itself is there. So if I go from IC to here counterclockwise, right? There's IB. So IB would be a IC, right? Then your IA would be A squared IC. So you can see that how it works, right? So with this factor over here, I can take everything and express them in terms of one current. So that's what is right here. So I'm going to use this factor into the equation we developed to find out the inductance. We can do this later in the class. So now come over here. So let's say your remember that your we already did it over here. So it's A squared IA. Your IC is AIA, right? So everything went to the IA now. You remember this equation from the last slide, lambda A, I'm gonna write it again here. Lambda A, it was 2 10 to the negative 7 IA ln 1 over R prime plus IB ln 1 over D12 plus IC ln 1 over D13, right? So now remember that IB over here and IC, you can express them in terms of current IA, right? So IB over here is A squared IA and IC over here is AIA. So if I put them over here and take the IA out, so then I can do one more step over here. So I can take the IA out and that would be ln 1 over R prime. Yeah, over here I'll get A squared ln 1 over D12 plus what I get A ln 1 over D13, right? Then if I bring this one on the other side here, divide, that would be my inductance for line A. That's what here, that's the inductance for line A, right? All right, then I can find the same equation for line B, line C, and line D. If I can write here for line B, I can follow the same format here. So for this one is IA. Remember the last slide we did. IA and IB is A, there's a factor A in there. So ln 1 over D12. And over here is IB itself, so is ln 1 over R prime, and IC with IA is A square factor is there, so ln 1 over D13, right? So now D13 or 23 for C, C2B is 23, sorry, it's 23 here. Okay, so now again, that's your LB. Then I can find LC same way here. That would be 2 times 10 to the negative 7 and this is your a squared 1 over d 13 plus is a ln 1 over d 23 plus is self over here r prime, right? So I have all the inductance for each line. To find the average inductance for all three lines, we're gonna space here for you to write it down. We're gonna take the average. It's called average taken average transpose line. So if we take the average and put them all together with the and, this is over here, and if we add them together, that's what you get, right? So, and that one, now you can basically rearrange this one here. 2 times 10 to the power negative 7, 3, or you can multiply 3 inside. Let's multiply 3 inside there. So if we multiply, let's to back here, 2 times 10 to the power negative 7. If you multiply 3 inside this here, this 3 will go away. So we have ln 1 over r prime here. Then we have all of this will have 3 over here now. Ln 1/3 d13 plus minus ln 3 d23 here, and ln 1/3 d13, right? We got all of this inside. Now these are all ln. We can manipulate this to simplify this equation over here. It would be 2 times 10 to the power negative 7. Over here you will have r prime over here. Over the top we have 3 d12 d13 d23, right? So that means this top here is called geometric mean distance between the line, and this is the GMR, geometric self radius. So I can basically simplify this as GMD over GMR. So geometric mean radius and geometric mean distance. If I modify this to simplify even further, 0.2 ln GMD over GMR, that is your millihenry per kilometer. All right. So that is the inductance for a three-phase line that is not symmetric. All right. Again, GMD is geometric mean distance between the three lines, and GMR is the geometric mean radius for line, and all the line we're assuming they have same radius, so we have the same GMR for all the lines. All right. That's all for today's this video over here. We're going to do some problem in the class. All right.